In this paper, we present an analytic framework for fast modeling and rendering of dynamic and non-homogeneous participating media. Such media can be characterized by density and velocity fields and are accurately modeled by the Navier-Stokes equations for fluid flow. The key idea in the paper is to express the density and velocity fields in the Legendre polynomial spaces. This results in completely analytic definitions of differential and integral operators, thereby avoiding discretization errors inherent in spatial methods. We now show different 2D Legendre space simulations. Notice that increasing the number of Legendre coefficients introduces higher frequency components, both in the density and velocity fields. Legendre polynomials can express interesting density and force distributions compactly. Here we show confetti being carried by a turbulent wind field. Notice the vorticities being created as a result of the turbulence. Here we show an upwards impulse on a smoke vase. The smoke diffuses when the force is removed. For rendering, we consider the single scattering model of light transport. Light rays first get attenuated and then get scattered once before reaching the viewer. Rendering in the reduced Legendre space allows the user interactive control over lighting, viewpoint position, and optical properties of the medium. Notice the variations in the shadogram with changing viewpoint, lighting, and density distribution. Changing the scattering albedos of the medium across color channels changes the color of the smoke and the shadogram. Here we advect the optical properties of the medium along with the densities. This creates the effect of mixing different media. In this example, we add non-homogeneous mist to a clear weather scene. Non-homogeneous distributions, for example, the high mist density over the lake, provide for more realism as compared to homogeneous mist. Also, notice how distant objects appear brighter due to the air light effect, whereas distant objects appear darker in the attenuation-only image. Decreasing the depth range of the scene decreases the variable air light effect. In this example, we show a fly-through of the Swiss Alps with non-homogeneous and dynamic fog added to it. Finally, we combine the effects of participating media and particulate matter carried by a fluid. First, we add snowflakes being carried by a wind field. We then add mist to the scene. Notice, further objects appear brighter due to the air light effect, and distant snowflakes become invisible as the mist density is increased. Here we provide the computational speedups of our framework as compared to spatial simulation and rendering.